And you will present this work about computational investigation.
Very long title, yes. So thanks for the introduction. It's also a big thank you for the organizers to organize this fabulous conference. The title is quite long. It reads Computational Investigations of an Obstacle-Type Shape Optimization Problem in the Space of Smooth Shapes. So quite a lot of topics which are mixed into one big problem. This project was also in collaboration with Mrs. Welker, who's sitting somewhere in the back there, exactly. Yeah, and to get a grasp of this problem, we will have to talk first about some basics of various disciplines. For example, variational inequalities and also shape optimization in general. And then we will formulate the model problem and see how we can solve this algorithmically. So just a short question for the audience. Who is familiar with variational inequalities? No one. Okay, so that's a good thing. So maybe I can motivate variational inequalities from variational equalities. So probably all of you are familiar with this very simple problem. Here you have an energy functional, and which you want to minimize over the space L2. And a very easy consequence of the structure of this convex functional is that you have a solution for this system or for this problem when you have a Gateau derivative which is 0 for all the inputs you have from the space, right? This is very basic optimization stuff, and this is kind of a necessary and a sufficient condition for optimality. And you can further rearrange this and get this system, which you can then variationally solve. Okay, and you can also manipulate the system, for example, by subtracting the solution itself, which is no problem since we have a big convex set. Every member can be represented in this fashion, and yeah, we're good to go. You can do the same thing, of course, for different other norms. For example, you can take these Sobolev semi-norms, right? And you can go on with the exact same procedure, and then you get a equation which probably is familiar to every one of you, yeah, the Laplace equation, as the optimality condition. Yeah? And the solution of this optimization problem is then the classical solution of the Laplace problem, the Poisson problem, depending on the right-hand side, and yeah, the usual weak formulation. Now, we can again do the same trick we have done before, as again we are in the same situation as we have been with the L2 space, but instead we have this Sobolev space, right? H1, 0. So it's fine too. And we can again generalize this even further. Nothing has really happened. We have just replaced the Sobolev semi-norm with the general bilinear form. Of course, very standard. We take a bounded coercive symmetric bilinear form. So we arrive at elliptic problems, which is quite nice, very nice behaved in most of the cases. And we can guarantee the exact same features we have just seen previously. Okay, now we want to get to variational inequalities. All this is a variational equality. As we can see here, you have an equality and you vary over test functions which are from H1. Now if we replace, you have to see the stuff in red. If we replace the test functions in the set over which we optimize by a convex set, which is, for example, a subset of H1, which is closed as well, the problem itself changes. So in general, the solution we will have then will not be the same as the one from the problem previously, right? For example, when the solution here is not part of your convex subset. Makes sense, quite easy. But still, as this is a closed convex subset and this is still a convex functional and you have lower semi-continuity and stuff, you will have unique solutions and the existence of the solutions as well. So this is quite easy. But there is one big difference. The optimality, as we have now a constrained optimization problem, is becoming an inequality. Right? Here, since we had the whole space, there was an equality, and now we have an inequality. And the problem to solve here is equivalent to solving this problem here, for which you can show that you have unique and existing solutions. Okay, and that's all. That's what variational inequalities of first kind are. There are, of course, more general problems, for example, variational inequalities of the second kind, which have some nonlinearities in there as well, but we will focus only on the type of first kind. And to further specialize this, you can pick a specific closed convex subset. For example, one which is defined by boundaries. Yeah, box constraints, you can have double-sided box constraints, or here we will only take a function which bounds all the possible functions from above. And this function, phi, is going to be from L2, and it's going to be called the obstacle. And this problem here is the so-called unilateral obstacle problem. So just to give you an idea where this stuff comes from, for example, some of you may know ketchup, right? Probably all of you know ketchup. The flow of ketchup itself is not Newtonian, since ketchup itself, it does not move when you want to get it out. But once there is a threshold which is crossed, it suddenly gets out pretty fast, and you have a mess all over your plate, maybe. This is exactly what is described by variational inequalities. So Bingham fluids is the term which is used there. Another problem which is quite famous is the so-called Signorini problem. Maybe someone has heard of it. It basically is the vector-valued analog of the problem we are going to look at later. And it describes how a shape, basically when you have a drop of water on a plate, you have a drop of water on a plate, and then you have gravity acting as a force term, and in the end you get the displacement vector field described by the linear elasticity. And since you have a plate on which the drop is resting, you can describe this as exactly a variational inequality of the first kind. So the plate here is something which is bounding from below, not from above, but the main idea is exactly the same. So I hope that is quite clear. Again, existence, uniqueness of solutions, all is guaranteed by the standard arguments. Okay. And there is now this theorem which is discussed in Ito and Kunish's paper, which is derived also by Guido Stampaccia as well. So it's quite older, but they just rediscuss it in a neat fashion. And we have an equivalence once we have additional regularity of the problem. So we can reformulate the variational inequality into a problem with an equality with additional constraints. So basically what we have here is an equivalent formulation of so-called complementarity constraints, right? So basically what you have here is a semi-linear equation with this lambda right here given by this nonlinear term here. Exactly, and what we have to put into this is that we have Lipschitzian boundaries, and as well that we have a regular obstacle. H1 is sufficient for this. Okay, and so we don't have to mess around with problems which are of variational inequality type, but we can then go back to problems which are a little more nicely behaved, where you can have equalities. And you can apply then standard techniques from the variational equality field as solving PDEs. All right, the main problem which is going to arise is that the second term here is arising from a Nemitzke operator which is not smooth. So you see here the maximum here, it's not a smooth function, right? And implicitly you have this y here for which we are solving, and you end up with a non-smooth equality. And this is mainly the biggest caveat and the biggest problem we are going to face once we start to do shape optimization. So have that in mind. And that's the main reason why we start to regularize this problem. And what we do for this is that we reformulate this problem to a kind of relaxed problem. And what we do for this is we smooth the maximum function. So there's this kink at 0, and we just smooth it in several different ways. We just use several different maximum functions. We tested in numerics in the paper here, which is also in collaboration with Volker Schulz from the University of Trier. we had several conditions for the maximum function, and one big condition is that it is C1, of course, the new maximum function that we look at, and also that we have uniform convergence outside an area of 0, where the original non-smoothness occurs. So we arrive at this problem here, and we also, don't skip that, we exchange the original adjoint here, the lambda. We exchange it by a randomly picked L2 function here. We exchange this, and we arrive at this equation, which can then be solved with standard problems, standard techniques, right? For example, you can take semi-smooth solvers, which was first done by Ito and Kunish as well, and they had superlinear convergence. So this problem can be solved with techniques already existing, so nothing new here. And what we proved here in the paper, in the proposition, is that this solution of the smooth problem converges indeed to the original problem in H1, so everything's fine. But again, we want to solve the original problem, right? We don't want to solve the relaxed problem. So what we will do in the following is we also prove convergences of the shape optimization problems and the solutions we had arising from the smooth problem. Yeah, and to visualize this, we see on the left a simple Laplace problem. The right-hand side is not of the matter. And on the right-hand side, you see the solution of a variational inequality. So, and as you can see, it's basically, it's just cut at the level of 0.5. And that's exactly where the obstacle is sitting. So in the right, you see the solution of the obstacle problem with the bilinear form being the one from the Laplace problem, but constrained over the set of all functions with a closer, lower or equal 0.5. So yeah, just a constant function bounding the Laplacian, the solution of it. Great, okay, so that's about it for variational inequalities. We will just shortly jump into the shape optimization regime. So what we do is, as we have seen yesterday in some other talks, we use the so-called BE space, which is proposed by Michor and Mumford and others as well. And what we use is we look at shapes which are embeddings from the S1 into a domain omega. We will actually look at R2, of course, because we want to embed S1 into R2 and see, look for manifolds of codimension 1. And we divide by all the reparameterization. So we cut out the diffeomorphism group of S1. Okay, and what Michor and Mumford showed is that this is a Fréchet manifold, and its tangential bundle can be characterized by all smooth functions on the boundary itself. Of course, this is abusive notation. Actually, we are looking at equivalence classes, but nevertheless, they all define the same image, so we are fine. Okay. And in order to get a gradient for the shape derivative we will later derive, we have to use a bilinear form, of course, in the fashion of Riesz representation. And what we use is so-called Steklov-Poincaré matrix, and these are derived by so-called Neumann solution operators. So what you do is you have a right-hand side, which you use as a force term, right, Neumann boundary conditions. And you have a given bilinear form, which is called A here. And you solve for the problem, and then you move back to its Dirichlet boundary. And you get the according Dirichlet boundary of the solution of the original Neumann problem. And you can go forth and back. Okay, but that's not of big importance. And you can use this Steklov-Poincaré matrix, you can use the Neumann to Dirichlet map, the inverse actually, and define a bilinear form on the tangential bundle of this shape space, and you end up with a metric called Steklov-Poincaré metric, which was done by Mr. Siebenborn, Mr. Schulz, and Mrs. Welker in 2016. So we will use this bilinear form to get gradient representations later on for the shape derivative we are about to derive. And yeah, here you can see the exact formula. This is nothing new. This is the regular gradient representation, which is seen everywhere. You have the bilinear form, and you also have the right-hand side, which is the shape functional, the derivative of the shape functional, which is also defined in a regular fashion. So you have the difference quotient, and the difference quotient. If it exists and if it is linear and continuous, we call this thing the shape derivative. Right? And we cannot apply regular difference quotients since we are operating this shape of spaces, so you cannot subtract or add shapes to one another. Does not make sense. What is a circle plus a triangle? So what we do is we use deformations. You can use the perturbation of identity for those of you who are into shape optimization, or you can walk along geodesics and then retract and look for the limit of the difference quotient. So that's what shape derivatives are. And the main problem for the model problem we're about to consider is, as I have mentioned before, the non-smoothness. The non-smoothness is the biggest problem since it's hindering us from having shape differentiability of the model problem we are about to discuss. So that's the model problem we have. It's the so-called obstacle problem constrained by a tracking type shape functional. So here you have a tracking type functional. We want to minimize over the shapes such that the right-hand side is put in gives us a solution which is tracking this y bar. So the y bar is the target we want to track. This is the regular tracking type shape function, optimization functional. And as I've told you, here's the problem. We have this maximum here, which is indeed giving us the non-differentiability. And this was proved by Mr. Sokolovsky, I guess, in 1998 or something like that. So this problem does not admit a shape derivative. And what we have done is we have regularized this problem, and we put in the smoothed version, and we were able to prove that the relaxed problem admits a shape derivative. Actually, this is only true for dimension n smaller equal 4, since we use Sobolev embeddings. But this problem is shape differentiable. And then you can apply all the machinery used in shape optimization. You can gain gradients, and then you can do optimization with steepest descent, or you can do LBFGS and similar other techniques. Exactly. And how we proved this, what we have actually done is we wanted to use the theorem of Correa and Seeger, which some of you probably no one knows about shape optimization, right? Not really? Okay, I see. So there are many big theorems which guarantee the that you have shape derivatives for a shape optimization problem. And one big theorem is the so-called Correa and Seeger theorem, where you prove several kinds of continuities, hemi-continuity, demi-continuity. We're not going into this, but we're not able to apply this technique for this problem. So we used a different technique called the averaged adjoint theorem, which was proposed by Kevin Sturm 2 years ago. And we were able to use this technique to prove the differentiability of this problem here. And it's essential that you have the differentiability of this max operator here. That's the main point. So without it, you're not able to prove it. And we also proved that for the adjoints arising from the regularized problem, we have convergence as well. So once you push the parameter controlling the smoothing to infinity, which gives you the unsmooth problem, you recover a limit object. Now, I have told you that the original problem is not shape differentiable. So we are not really able to get real adjoints and real derivatives. But nevertheless, we arrived at some limiting object. And now we are not really sure what type of limiting object we have. And this is part of the further research. We are going to look at what kind of optimality system we had in the limit. But nevertheless, you can use this object for the optimization, and have kind of a heuristic for the shape optimization algorithm. Yeah, and we also had closed formulas. So it was interesting that we could arrive at a formula which is very easy to solve and which admits sparsity structures for a set called the active set. Everyone who knows about variational inequalities is familiar with this term, but for you this is just a set where the solution of the variational inequality is at the obstacle, right? So for example, when the drop is at the plate, you have this contact area, that's the active set. And on this active set, actually, the limiting object is 0, which gives us an algorithm which is able to exploit further sparsity the closer the obstacle is pushing the solution to 0. Yeah, and here we have some pictures how a shape optimization algorithm looks like. So we had an obstacle here, which is pushing very low here. And the dotted line is a target we want to approximate from the tracking type target function we were talking about. And we started with this circle on the left, and we descended with the gradients, with the negative gradients, and we were not able to go closer once we crossed or once we got to the obstacle, right? And this is due to the fact that the adjoints I have just told you about are 0 there, so you don't have any information where the obstacle is, exactly. Yeah, and something curious happened during the LBFGS we have applied. Actually, we arrived at this, at the shape, or mostly at the shape we wanted to track, which was pure luck, because the steps were very big and you used a step previous to the final step, which had still the adjoint information on the area which was not 0. Exactly, and also we have, of course, seen that the LBFGS is faster. Yeah, and that's about it. So, thanks.
Okay, so any question?
I have a question. Can you characterize the error between the solution with fixed C and the true solution?
Yeah, that's a good question, yeah. We're actually looking at this and we are very confident that we can do so. We have not done this in the paper which talks about the relaxation. So we have only the convergence of the shape derivatives to a limiting object, which is not a shape derivative since the original problem is not shape differentiable. But yeah, we are very confident that we can use techniques from Delfour and Celesio, if you know them. Yeah, some French shape optimizers. Yeah, and apply these techniques into this framework and then recover exactly this. But we have not proved it yet. So yeah, good question.
Any other question? Okay, so let's have a speaker again.